Thank you very much, everyone. Thank you, Waterloo Blockchain, for having me. My name is Marston Connell. As he said, I'm the co-founder and CTO of Jackal Labs. We're a Canadian-based startup working on decentralized cloud storage. You're probably used to cloud storage being kind of these more centralized entities. AWS, your iCloud, Google Drive, the stuff that you're familiar with. But there's a lot of problems with these cloud storage solutions. The big one, they're centralized. It means that all of your data is on their systems and theirs alone. They can lock you out of your data anytime, just for no reason at all. If they deem what you're saying or what you're storing to be against their terms of service, they can shut you out. They can delete your entire account. Your data can just go missing at the drop of a hat with really no recourse for you. On top of that, you got to trust all these things, right? You upload your personal information, whether that be like important contracts, personal photos that you don't want anyone else to see. All of this stuff is going onto their systems fully open, unencrypted, which means that anyone that's, has access to your data, like employees of these companies, they can just see your data. They can go in, they can mess with it, they can do whatever. So you have to really trust these companies that you're giving your data to. On top of that, kind of going back to that first point, they're not censorship resistant. So if you're, a journalist, let's say, and you're posting opinions on your home country that's a fascist government, if one of these cloud platforms are operating in that country, they can be subpoenaed, which means they can go in and they can take your data down because it's against what the government mandates. And the last thing that you're probably hearing a lot about is like data mining. So whether that be for advertising or more currently, artificial intelligence, all of these companies are taking your data and they're running their either AI models or advertising models on them and selling that either the data itself or the models that they're generating through advertising or AI models. And you're basically just handing them all of your data for free. You're getting nothing out of it except a little bit of free storage. That's kind of the thing, storage isn't free. Storage has to be stored somewhere. There's a lot of overhead. So anytime, that classic is it's free, then you are the product, couldn't be more true with cloud storage. Decentralized platforms store your data better. And I say better because I mean better, not subjectively better. It stores your data in a way that is truly, truly yours. Let's go over that word decentralized a little bit. What does that mean? Because is AWS decentralized because they have servers all over the world? My definition of decentralized might be a little bit different from theirs, but I'm not talking about just geo-distribution. I'm talking about full top to bottom ownership of your data. There's no middleman involved. It's truly owned by no one. So decentralized storage platforms, they're like any other cloud storage. They have issues that arise, and in order to make them scalable and safe for you to use, we have a few things to overcome. And a lot of these decentralized storage platforms today are doing just that. What are these pitfalls of decentralization? The big one, probably the most important one, is verifiability. If you're with AWS or with Google Cloud, you're giving your data over to AWS or Google Cloud. You know that your data is being stored with this one company, and you can kind of trust that they will hold onto your data because they have incentives to do so. They have a reputation to hold on to. In decentralized storage, anybody can provide storage. It doesn't matter. You don't know necessarily who's actually storing your data. And because of this, there needs to be ways for you to verify that they're actually holding onto your data. Because if I was to spin up a storage provider, offer my services to this decentralized storage network, I could say, hey, I'm storing your data, but in reality, I'm storing nothing, making money for doing no work. So we need a way to overcome this. Second, really big issue is scalability. Decentralized platforms don't have the funding of a full integrated Web 2 company like Amazon. So, we're not able to control the machines that your storage is running on, right? So AWS can put top of the line data centers in. If you go to AWS and say, I need the best of the best, they will give you the best of the best because they can guarantee the best of the best. Decentralized platforms, again, because you don't know who you're dealing with, you can't verify any of this. So scalability becomes a real challenge because you need to put incentives in place to do better. The last, still very important thing is insurance. So much like verifiability was assurance, insurance is really important because what happens if your data disappears? And it inevitably will. A hard drive doesn't last forever. In traditional Web 2 platforms, you've got backups. If you go to Amazon and their server fails, well, they have 2 more servers backing up everything, right? You can kind of guarantee that if your data goes away, either it's backed up or you can sue Amazon because you've made a service level agreement with them and you know who you're dealing with. But again, decentralized platforms, you don't. So let's start with verifiability. If we don't know who's storing the data, how do we make sure it's still there? And that is probably the most important thing to overcome with decentralized storage. And the answer is Merkle trees. We're going to talk a little bit about what a Merkle tree is and kind of how they work and how they relate to cloud storage. So this is a diagram of a Merkle tree, right? So at the bottom there, that is our file. When you want to create a Merkle tree of a file, you split it into a bunch of little chunks. So you can imagine, if this file is 8 kilobytes, each one of those little chunks at the bottom is 1 kilobyte. I've lettered them here so that we can, refer to them. But essentially what a Merkle tree is it uses a hashing algorithm. So it takes 2 nodes at the bottom, hashes them together and creates a new node. And then it does the same for all of the nodes. It then has, a new layer above it, and then we hash those together. And we hash them all the way up in pairs until we hit the very top, which we call the root. So if you kind of picture it, flip it upside down, it looks a lot like a tree, with all of those pieces of the file being the leaves. If we want to go ahead and say, I want to prove that this piece D belongs in this file, right? Because that's really cool. If we can just take a singular piece of this file and prove that it belongs, well, we can start to work on that verifiability problem. So if we take D, we can build a proof structure, which, because of the way the Merkle tree is built, only requires C, I, N, and the original piece D to be kind of packaged together into a proof. And then we can use the root to verify that it's there, because we can rebuild the tree from just those pieces. This is kind of what Jackal does here. We take, that same approach, but we need ways to kind of manage which pieces we're looking at, right? Because we don't want them to just be able to prove the starting piece over and over and over again, because then they only need to hold on to the starting piece. We want them to hold on to the whole file all the time. So our approach is we use random sampling. Over the life cycle of a file, what we can do is if we randomly select these pieces, the storage provider that's holding onto this file won't know what piece needs to come next. And if we sample enough of those pieces, they will need to eventually hold on to all of those pieces and prove all of those pieces at some time, and they won't know the order. So at that point, it becomes more work for them to offload pieces that they're not proving and then pull them back when they do need to prove them, because they never know what piece is coming next. On top of that, we now need to index these pieces because, a Merkle proof with the root can be valid. If I give it piece A, even though they're asking for piece D, unless I have a way to prove that I'm giving them piece D, the blockchain that's like verifying these proofs won't understand, that it's an incorrect proof. It'll still verify it. So what we do is we index all of them. And then we hash piece A, with index 0, piece B with index 1, piece C with index 2, and so on. And this creates basically an entire new tree. If you chop off that whole bottom, that's your standard Merkle tree. So what we do now is, because we have all those new pieces, right? You're thinking, well, if I can just use those pieces to prove the Merkle tree, what's the point in me even storing the files originally? Why can't I just store the hashes, right? This is where the blockchain comes in. And the blockchain enforces a very specific set of rules. So this is kind of an example of that blockchain data. So this is what a file looks like on the Jackal protocol, metadata-wise, right? So we've got the Merkle hash, which is that big long string of characters up there. And that's the root that I've been talking about this whole time. And then we also have these proof objects, which these two are examples of proof objects. Those are identifiers. And then we carry them over to this. And you can see that data matches right there. That Merkle's the same. And we ask it, which chunk it wants to prove. And that data, that index for the chunk to prove adjusts over time and is randomly selected out of how many chunks fit in that file. So if we want to choose, we want to verify chunk 1, right? That's B, right? From here, we don't just send J, because, that's where the Merkle tree starts and everything, and that's all well and good. But if we send that to the blockchain's rule set won't allow that. What the blockchain does behind the scenes is every time you send up piece B, it's going to know, because it has it on that blockchain, that we're looking for index 1. It's going to then take B that you've sent it, hash it together with index 1, and then start the process from there. So you do need to actually send it this bottom layer, because it creates that secondary layer on the fly as it's verified. And same thing goes, we can send it B, we can send it I. We don't need to send it A, because that's not what we're proving right now. And then we can just send it all of those other pieces. It rebuilds the whole root, and then we can verify that B was indeed a piece of that file. So that kind of covers like how we verify that data. We randomly sample that data over and over and over again, and eventually we can prove that that file's there. What's the point, right? Why do we even prove it in the first place? Well, that's another really great spot where the blockchains thrive. It's where blockchains really excel at this, and it's the token layer built into the blockchain. What we can do is we can create these deals on chain that you just saw, and we can tell the storage providers that if they continue to prove those deals, we're going to pay them in tokens, right? So on the Jackal protocol specifically, you hand the protocol your tokens. Those tokens then get put into a big account that keeps track of all of your payment information. And then as storage providers prove those files over and over and over and over again, they get drip fed those tokens. So the more files they're proving, the more money that they actually make from the protocol. Scalability. Scalability is a huge, huge issue, especially in blockchains. And basically, the proofs are really big. If we're talking about a file that's those 8 kilobytes and we're using those chunks, we have to send up a whole kilobyte every time we want to do that proof. That sucks because the proof, depending on how big your file is, the proof scales with the size of the file, and you're sending that original piece as well. So blockchains have limited bandwidth, right? There's a maximum amount of block size, and you don't want to be filling that with that file piece that's going to be proven over and over again when you might not need to. We can take a look at some existing solutions and kind of what's been, done. And if we look at something like Filecoin, they currently use ZK proofs. So what that allows them to do is have a very small proof footprint, and they can prove very large chunk sizes without needing to do a lot more work and use up their bandwidth. Like on the Jackal protocol, if we were to send a whole proof up and the proof chunk, right, was 10 kilobytes, you're sending a whole 10 kilobytes up. So that scales, and you can only fit so much on. The cons is if you're using really, really small chunks, a raw Merkle tree proof is generally going to be faster. Because it's all decentralized, you're doing the same ZK proof computations across every node in the network, which can get expensive. And on top of that, they still use a bit of bandwidth, right? They're still a proof that you're sending up and verifying. So although they're smaller, they still exist. We can look at off-chain verification as well, which is something kind of like what StorageAid does, where, they're not doing that decentralized verification. They're looking at taking that data, storing it on a decentralized set of nodes, and then making sure that their central system is keeping track of who has what at what time. This is really fast, really, really, really fast. It has almost no overhead. As I say, it's not decentralized, so you don't need multiple nodes running the same thing. It can basically scale infinitely, and it can prove any size pretty much instantly because, again, they can scale their hardware with however much load they want. The big con, which makes it pretty much unusable for any truly decentralized platform, is it relies on trusting a third party, which that trust layer is what we're trying to get rid of, right? We've done something a little different. We've created this solution that we call consensus spheres, and it's a really, really interesting way to kind of get around those two systems while almost combining them in this fun way. So, the blockchain is a consensus layer. It's a bunch of computers that are all agreeing, right? If we go ahead and every time we want to make a proof, one of the storage providers says, hey, I want to submit a proof. The chain, all of the nodes can come to agreement. They can create a small little list of other storage providers. This we call a sphere because it's just a group of storage providers that are going to talk to each other and verify that they are coming to consensus. So it's almost like, if you have a big ring diagram of the current validators on the network, it's creating little rings off of the big ring, which is really, really cool. Then from there, the storage provider, when they go to make that proof, they send the proof to the storage providers. So that proof never even makes it to chain. So this is kind of going back to that off-chain computation that we were talking about earlier, where they're sending their data to the storage providers that are part of that new sphere. And then those storage providers verify that proof themselves. And because of these storage providers are generally doing less work because they're not managing the overhead of the actual blockchain itself, they can compute, they can verify these proofs a little bit faster. They won't be using up the bandwidth of the chain. And then from there, they all come to consensus, which is why we call them consensus spheres. So once that little group comes to consensus, they all send an attestation to the blockchain itself saying, hey, I verified the proof, you picked me, we all kind of agreed. And what this does is it basically allows us to reduce the overhead of sending an entire proof to the network to just a simple one-liner message saying, I would like to create a proof. And then it's basically just 3 by default, or however many the chain actually chooses, Boolean true or false value saying yes or no, this proof is valid, which reduces the overhead by a lot. And on top of that, the system's really, really great because it can also run in parallel with just the traditional proof system. If the consensus spheres fail, we can always roll back to like original proving mechanisms per file. So, if this isn't like the whole network shuts down, it's just basically if, your one proof, if for some reason all the storage providers that get picked go down that instant, you can always post the proof. And that's kind of where, we might switch to ZK proofs as well to make those proofs even smaller. On top of that, because it's blockchain and, we all love roll-ups and stuff lately, there's kind of another scaling solution that we can use, which are child chains or, I guess, roll-ups. And what that means is, the core Jackal blockchain will verify your proofs. It'll manage all your storage deals. But, that main chain has limited bandwidth. So what we can do from there is just kind of horizontally scale them out. We can create more blockchains, which means more bandwidth. And then using zero-knowledge proofs for scalability, we can shove a whole lot of like attestations from one of those child chains into a single transaction, verifying that everything was true. And on that main chain, we can delegate all the rewards to the storage providers. But that main blockchain doesn't need to handle all of the load. So our last kind of pillar there, insurance. So what happens when things fail? Because they're always going to fail. Everything in the computing world fails, right? Computers get old, hard disks fail, even solid state drives fail. What do you do about that, right? And I kind of mentioned that in Web 2, you can kind of sue the storage provider that you're currently using because you have service level agreements, or you can tarnish their reputation. But in Web 3, that's very, very difficult because you don't actually know who you're dealing with. So you can really do nothing. Most of the blockchains that exist today, Filecoin, Arweave, Siacoin, if your file disappears, it's gone. There's nothing you can do about it, which is really, really crazy when you kind of break it down. You're expected to go in and kind of create your own redundancy. So, if I want to upload my file, I upload it like 10 times because I just am hoping that surely not all 10 storage providers are going to die before my file deal is expired. Here at Jackal, we said that's ridiculous, right? Like we want to service businesses. We want real people to be using cloud storage in a decentralized manner. And so we created two protocols that we built in, JPOP and IDLE, which stand for Jackal Proof of Persistence and Internal Detection of Loss. We're currently the only blockchain that actually does this in decentralized storage. And essentially what it does is the proof of persistence manages redundancy on the blockchain. So what that means is if you upload a file, we actually create 3 copies of that file so that if a copy ever does go down, you have 2 more. And then, storage providers, if there's only 2 copies on the network, they can go and they can claim that empty third spot and remake that deal, download the file from the other 2 storage providers, and boot right back up to 3x redundancy. So you don't have to manage your redundancy at all. On top of that, you can choose your own redundancy. If you want to pay for more redundancy, you can pick 10 copies, you can pick 20 copies, and you can pick 1 if you're feeling really, really ballsy, And then the internal detection of loss, that's kind of the way that JPOP manages to know when those files are down. Back to that verifiability, when those storage providers are making those proofs over and over and over again, the chain actually knows, hey, this storage deal hasn't had a proof submitted for like 12 hours. Probably means the storage provider is dead because it's supposed to be submitting those proofs. The blockchain knows this because it's, we use a Tendermint blockchain, so it's really, really fast. It can do a lot of computation in a really short amount of time compared to like old blockchains like Bitcoin or Filecoin. And from there, we can take that and we can actually tell the chain to kill that deal with the storage provider because clearly it's not doing its job. It's at that point that a new spot opens up and then the persistence can take over and fill that spot. So, this is a fully decentralized, permissionless way for you to manage redundancy, for you to have insurance on your data, and to manage what is essentially a Web 2 way of dealing with backups in a Web 3 setting. Decentralized storage is maturing. It's never really had redundancy. And so Jackal creates that same file over and over and over again. And, JPOP and IDLE manage everything for you. Decentralized storage is getting a lot better. I've been talking about, Filecoin, Arweave, Siacoin, and how none of these platforms have any sort of redundancy or insurance at all. And, they're only, Filecoin's only 7 years old. It started in 2017. So it was basically a toy when it launched. It wasn't really, it was kind of a research project that wasn't expected to hit mainstream adoption. And so this is why Jackal, we've positioned ourselves as a platform that's modular and expandable, because we want to take what companies like Filecoin and Sidecoin have been doing in the research space and bringing it to life that can service everyday regular people. We only have 5 years difference between us and Filecoin. And when you think about like what 5 years actually means, that is not a long time at all, especially in computing. Stuff happens so quickly, but in such like strange amounts of time. And we're really, really close to making that Web3 data storage feel like Web2 data storage, creating those developer libraries to make integrating with like AWS systems really, really easy, or even just having like a photo backup on your phone. It's not possible with Filecoin or any of these other decentralized platforms. It's becoming more of a reality with these kind of modular chains like Jackal. So what is the future of decentralized data? It's having that full self-custody. It's being in control of your data. It's decentralizing as many of the working parts in a cloud storage network, so that that your data is only being seen by you, it's only being accessed by you, it's only being controlled by you, and can only be deleted by you. On top of that, we're talking a lot about interoperability. So, you're talking about blockchains interacting with each other, but more importantly, blockchains interacting with other services like existing Web2 solutions. Not everything needs to be a blockchain. And so we need to interact with non-blockchain platforms. And so we're starting to see a big shift into kind of these like Web2 platforms, integrating Web3 systems, and making sure that your data is yours even on those systems. On top of that, when we're talking about interoperability, if we have kind of like a great example is the medical field. If you have medical records that you want, you got to go and you got to call your doctor and say, I want these medical records transferred to my new doctor, right? That sucks, because that means your doctor has full access to them. And although it's against the law, in theory, they could just go and shred all your documents and you wouldn't have them anymore. What decentralized storage allows you to do is it allows you to take that data, make it fully private and secure, share it with your doctor. And if at any point you want to revoke access and switch to a new doctor, they can update your data. And then the second that you want to switch, you block them out, you move your data over, because it's all yours, which kind of goes back into that self-custody. On top of that is privacy. Going back to it, I haven't really touched on it, but Jackal's currently the only decentralized storage platform that has built-in privacy, which is pretty crazy to think about. You're uploading stuff to like Filecoin or Arweave. That's public for everyone. Somebody can just scan that network. And if you're uploading, a service agreement with somebody, photos of yourself that you don't want anyone else to see, you can't use any decentralized storage platforms except for Jackal today. And that's getting a lot better through Jackal, and kind of making it easier for you to have that privacy and integrate sharing of files and everything, and make it feel very much like a traditional Web2 company where you have those like sharing abilities. And then on top of that, decentralized storage right now is kind of slow, compared to Web2, because again, it has to come to consensus. It's dealing with blockchains. We all kind of know how slow blockchains are today. Decentralized storage can only get faster. Consensus networks are going to get better. They're going to get faster. Hard drives are going to get faster. We're going to parallel compute a lot more, making things much easier for you, the end user. And then lastly is better portability. So, creating better standards for decentralized data so that you can use your decentralized data in more places. If you're, playing like a video game and you've got assets in your one game, you can kind of bring them over because they're all the same standards. And so creating those standards, creating that better portability experience for you bringing your data places is really big on the to-do list of future decentralized data endeavors. So that's it for me. Really appreciate you guys coming out. As I said, we're Jackal. We're a decentralized cloud storage company. And if you want to reach out, that's my email, that's our website, and that's our Twitter. So yeah, thank you. Oh, I guess, does anybody have any questions?